Well, our first example is to construct a slope field from the differential equation dy dx equals x plus y. So the isoclines would be like x plus y equals some constant c. For instance, x plus y equals 1, x plus y equals 2, x plus y equals 3. And they would be lines with slope -1 and parallel to each other, of course. And so along those lines, like maybe where x plus y equals 2 would be maybe somewhere along here, and at this particular point, when x is a half and y is 1, let's say, or maybe y is 1.5, then x plus y would be 1/2, let's say, plus 1.5, so 2. And so the slope of this lineal element here, the dy dx, is 2. And if we were to say, what about where x is 1/2 and y is 3, then the slope of this line is 3.5. Sorry, I shouldn't say line, I should say lineal element. And that's the way to construct all these line segments. You can do these by hand, but to get one that has this many line segments on it would take you a long time. But to do 20, 30, maybe even 40 line segments wouldn't take you that long. Just to show you, for this one, x is a half, y is 0. So x is a half, y is 0. That means the dy dx at this point is 1/2. See, you can see that pretty easily. I didn't have one drawn here. This is actually drawn with software. But if I would have, the slope right here would be 1, precisely 1, because x is 1. So 1 plus y is 0, so dy dx would be 1 plus 0, so the slope right at 1 would be slope 1. A lineal element, there we go. Lineal element would be right there. Do you understand this?
No!
Well, I'm really sorry. Should I explain it again?
No!
Alright, well then, we'll just go on and say, once I've gotten my direction field, then we might be able to draw a few functions on here. For instance, if I started here and tried to keep it touching tangent lines, right, well, I'd draw a function that would kind of fit in here like this. If I started going this way, you see, I might get a function that started to turn a little bit south. If I started straight on, eventually I'd hit a tangent line and maybe come back north again. See the way these tangent lines would be steering the function north. That's what the slope field does. The slope field allows me to guess the graph of a solution. Now, of course, if I knew an initial condition, I'd say, it's the one that passes through here, so maybe I would draw this one, like that. But here, if you'd like to see it, is a picture of a few functions drawn on this vector field. Would you like to see it?
No, no, no!
Well, we're going to anyway. So, I don't know if you can see like the functions on here. See how the function seems to be touching the tangent lines and kind of maintaining a point of tangency here, like this one right here. This one, well, that's not exactly a point of tangency, but you can see it's very close to the correct slope. And these are all like that. They all kind of come in, they follow the correct slope. They all sort of start right here. I wouldn't have to do that. If I started one here, it would go and be off the map. If I started one here, it would be off the map this way really quickly. So here's a MathCAD view of the same problem and also solution using Chapter 1 methods and a few drawings. So if you'd like to see the same problem, and here's how you do this with MathCAD, here's the thing you would change would be right here, the x plus y. Although I've messed around with all these different things that can be changed, you have to actually use a complicated system to graph it. I'm glad somebody else figured this out and I didn't have to figure out how to use MathCAD to do this myself. But here is a slightly larger picture. Actually, I think the size is pretty much the same. Yeah, -4 to 4. So it's just, I've got more lineal elements on this picture. So there really is one at 1, 0 here with slope 1. So, and I actually solved the equation since it's a linear first order, right? That was easy. And so, the integrating factor e to the negative x, and so therefore the you know, once I found the integrating factor, I did that here. Actually, no, I did that, and then I multiplied by e to the negative x both sides, and then I said, well, that's the derivative. I got these in the wrong order, but you're getting the idea. Are you getting the idea now?
No, no.
Oh, sorry. Well, you should get this idea because I'm just doing something from chapter 1. So then, since the derivative of this side equals this side, if I integrate both sides and then multiply both sides by e to the positive x, you would get this solution. Y equals, you know, trust me, if you integrated this, this would be negative x minus 1 times e to the negative x and then plus a constant of integration. Then when we multiply both sides by e to the positive x to make up for this, we would get y equals negative x minus 1 plus some constant times e to the x. Now, back up here to our, did I already do that? No, I didn't do that. So back up here to our function. I think with care, I can put one of those in. When you say one of what, well, I got the function here, right? This is the function. The only thing is I don't have a c. So if I say, let's see, let's put in c equal to 2. And so I'll take this function and go up here and paste it into my graph of my, there we go, this is the graph. I don't know what this part and this part's all about, but this part you can kind of see, right? It fits in there with the lineal elements pretty well, and this would be an example of the graph of a solution to this differential equation. But for a different value, if I put in, let's say 4, what happens? Well, there's a different one. And if I put in, let's say, negative 3, then I get, you know, some of the perspective curves that might go in this direction. And if I put in, let's say, 1/2, then I get the curves that might have come down here like this. So I'm just trying to show you how these curves are potential solutions of this differential equation. Now, if I had an initial condition, like if I knew the graph went through this point right here, then I'd say, oh, pick this one. That would be the graph to pick. And that would, you know, that would enable me to find, you know, same thing. If you get an initial condition, you can find for that constant, whatever it may be. I've just been making some up here, but here's another one, and maybe another one will make it 1/10. This ought to be interesting. Yeah, it goes down here and then comes back up, so you can kind of see this is an accident and this is an accident. They're not supposed to be there. I'm not sure exactly how the slope field is drawn, but because of the weird way the slope field is drawn, you get some extra stuff besides the function itself. Not sure why or how it does that, but hopefully you understand that. Do you?
No.
Sorry, but you know, would you like to see another discussion of this video?
No.
Okay, well that's it then.